Hello, we are coming to the end of our chapter on statistics. We're in the last section, section 6, and there are two main ideas in this section. One is confidence intervals, and one is hypothesis testing. These are basically ways that we analyze the data that we have compared with the mean and make some assumptions about the population. So what we've been doing up until now is applying what we called our standard normal distribution and our z-values to some data. Today we're going to take those ideas and we're going to apply them to finding confidence intervals for normally distributed data, and we're going to perform what we call hypothesis tests on normally distributed data. So there's a lot of new vocabulary in this section, so make sure that you're paying very close attention to these things. The vocabulary, the wording, understanding the concepts is going to be really important to understanding and being able to apply this section to statistics. All right, so we're going to start with confidence intervals, okay? We use confidence intervals in something called inferential statistics. Basically, inferential statistics are statistics that we use to draw conclusions, or another way to say that is statistical inferences. We're inferring something about a population using a sample. So we've talked in this chapter about samples. If you can't test a whole population, you test the sample. But then what I can do is use statistics, specifically inferential statistics, to take my information from the sample and make inferences or conclusions about the whole population. One way we do that is with something called a confidence interval. A confidence interval is an estimate of a population parameter, and it's basically a range of values around my mean. This range, what we're basically doing is we're using our sample mean, and we're getting a range of values around it. So we're saying we have some value, and my mean is between this range of values, and we're saying that our population mean will fall somewhere in that range, or that's what we want. We're saying how close, basically, is our sample mean to the mean for our whole population. It's equivalent to the area under our standard normal curve. So we usually do confidence intervals either at 90% confidence, 95% confidence, or 99% confidence. And it's equivalent to the area underneath the curve between these z-values. So these are the basic z-values that we'll use for the different confidence intervals, depending on what level of confidence we're looking for. To find the confidence interval, we use the sample mean, which we already talked about, and we use something called the maximum error of estimate. The maximum error of estimate is the maximum difference, or the biggest difference, between the estimate of the population mean and its actual value. So we get an estimate of our mean, we get our sample mean, and we have our actual population mean. The maximum error of estimate tells me what the biggest difference is between the real population mean and my estimate that I got from my sample. This is the formula that we use. Z is the z-value for a particular confidence interval. S is the standard deviation of my sample, and n is the size of my sample. And n has to be greater than or equal to 30, notice. So my sample size has to be at least 30 or greater. So I use z-values, standard deviation, and the size of my sample to get an error estimate for what's the maximum error, or how far off would I be maybe? What's the farthest I can be from my actual mean based on my sample mean? So let's take a look at this example. A poll of 422, that's my sample size, randomly selected adults showed that they brushed their teeth an average of 11.4 times per week with a standard deviation, S, of 1.6. We're going to use a 99% confidence interval, so that's going to be the third one that you saw in the picture, to find the maximum error of estimate for the number of times per week adults brush their teeth. So if we look back at the picture, this is my 99% confidence interval. Notice my z-values here and here. Those are the z-values we're basing this on. And that's why they put that z-value here, because we're using a 99% confidence interval. So then we just plug into our formula. There's our z-value, our standard deviation. There's our sample size. We just plug and chug, and we get about 0.2. This means, because we did a 99% confidence interval, you can be 99% confident that the number of times per week that adults brush their teeth will be within 0.2 of my sample mean. So 11.4 was my sample mean. This maximum error of estimate means the farthest off I can be is 0.2 in any direction. So I could go up to 11.6 or down to 11.2, but I can be 99% confident that my actual mean will be in the range from 11.2 to 11.6. So that's my maximum error of estimate. So you guys try it with this one. All right, your answer here should have been C, 0.96. Here's the work that backs that up. Your z-value is 1.960. You should have used from your note guide the z-value for the 95% confidence interval. 9.6 is my standard deviation, and 385 is my sample size. So this means we can be 95% confident that the population mean, my actual mean, will fall within 0.96 of the given mean, 39.3 minutes. All right, so the actual confidence interval is when I take my, my sample mean and I add and subtract the error, which is kind of what we've already been talking about. So X bar is the sample mean, E is the maximum error of estimate. So the actual confidence interval is the range of values. So let's look at what we mean by that. Here it says a poll of 156, that's my sample size, randomly selected members of a golf course show that they play an average of 4.6 times every summer with a standard deviation of 1.1. We want a 95% confidence interval for the population mean. So again, my confidence interval, notice here, this is just the formula we were just working on, maximum error of estimate. So here's my mean, 4.6, my sample mean, and here is the work for getting the maximum error, maximum estimate of error. So my range of values, because what I get when I calculate E, which is what we were doing in the first example, is 0.17. So basically to get my actual interval, my interval is between 4.43 and 4.77. Why? Because again, I took my mean, my average, and I added my error of estimate, so that's the farthest it can go above that, and 4.6 and subtracted my error estimate, and that's the farthest it can go below. So this is the range of values. I can be 95% confident that my population mean, the actual mean, would be between these two values. Okay, you guys try this one. All right, mu, which again is your population mean, should fall between 6.62 and 7.18. All right, and here's the work for that one. So notice what I chose to do was to first find my maximum error of estimate, which I get is 0.28. Again, z-value for a 90% confidence interval, so make sure you got that right one from the picture. Standard deviation over the square root of the sample size. I got 0.28, rounding to the nearest hundredth. So then I take my mean, my sample mean, and I add my maximum error of estimate, so 7.18 would be the upper end of my range. And I take my sample mean and I subtract my maximum error of estimate, and 6.62 would be my lower range. So this means I can be 90% sure that my actual population mean would fall between these two values. All right, now we're moving on to the second part of this section. We'll get as far as we can, and this is called hypothesis testing. So basically what a confidence interval does is it gives us an estimate of the population mean. So I'm saying, okay, my sample mean was 6.9 years, but I only polled or talked to 114 people in a large corporation. There's a lot more than 114 people. But I got an average of 6.9 from them. This range gives me an estimate of what the actual mean or the actual average would be if I was able to talk to everyone in the large corporation. I can, with 90% confidence, say that the actual mean would be in this range. So this is an estimate. That's what the confidence interval does for me. A hypothesis test, which is the next step we're doing, is going to assess or judge or give us some information about a specific claim about the mean. So this word claim is going to be important. Normally, we claim that the mean would be equal to something, greater than something, or less than something. So usually we're just claiming the mean equals this, the mean is greater than or equal to this, or less than or equal to this. So a hypothesis test has two parts. It has something called a null hypothesis, which we describe with H sub 0 or H naught. It's a statement of equality to be tested. So the null hypothesis always has to have an equal in it. Either it's an equal sign or less than or equal to, greater than or equal to. So wherever the equals is always going to be the null hypothesis. Then we have the alternative hypothesis, which is always the complement. So if we say the mean equals 3, the alternative hypothesis would be the mean does not equal 3. The alternative hypothesis has to include all the other information. And the alternative hypothesis is a statement of inequality. So it's going to be less than or greater than or not equal to. Okay? So the null hypothesis has to be equal to, less than or equal to, or greater than or equal to. Alternative, less than, greater than, or not equal to. And our claim, the claim that we make about the mean, can be part of either one of these. So we have to pay super close attention to where our claim is. So let's take a look here at this example, and we're just going to practice identifying the null hypothesis, which has to have the equals in it, and the alternative hypothesis, and figure out which statement has the claim in it. Okay, so Cindy thinks that her employees spend over 60 minutes per day surfing the internet at work. So over 60 minutes, we're saying that she thinks the average, or her population mean, is greater than 60. Not over 60 minutes would include everything else. So we're going to have two statements that completely complement each other. Either the mean is greater than 60, or the mean is less than or equal to 60. There are only going to be two options, and they have to include everything. So the claim, she's saying her claim is over 60. So the claim is going to be here, that the mean is greater than 60. It has to be the alternative hypothesis. This has to be HA because it doesn't have the equals. Remember, we said that the null hypothesis, H sub 0 or H naught, has to include the inequality. So our null hypothesis is that the mean is less than or equal to 60. And our alternative hypothesis is that the mean is greater than 60. How do I decide? The null hypothesis, always has to have the equality. The alternative does not have the equality. So we would say H sub naught is that mu, or our population mean, is less than or equal to 60. H sub A, mu is greater than 60. And our claim is in the alternative hypothesis. Let's take a look at another example about Mr. Bacon. Mr. Bacon thinks that he tells at least 5 jokes. So that means he thinks that the number of jokes he tells is greater than or equal to 5 every class period. Okay? That's what he's claiming. At least 5 jokes, that's how we write it, that the mean would be greater than or equal to 5. Not at least 5 jokes, everything else, mu is less than 5. So this time, notice that my claim is right here. This is what Mr. Bacon said. And this has to be my null hypothesis because it includes an equality statement. This has to be my alternative hypothesis because it does not include an equality statement. So our null hypothesis is the mu, or our population mean, is greater than or equal to 5. And this time, notice my claim is in the null hypothesis. In the last example, my claim was in the alternative. The claim can be in either place. Okay, the claim can be in either hypothesis. You just have to identify which it is. And my alternative hypothesis is that the mu would be less than 5. So the alternative hypothesis says, no, Mr. Bacon tells less than 5 jokes per period. All right, here's one for you guys to check out. All right, your answer here should be D. Angeline thinks that the manuscript can be produced in no more than 14 days. So less than or equal to 14 days. That's why that's the null hypothesis, because it has the equal to. That's also what she's claiming, right? Identify the null and alternative hypothesis. So if my null hypothesis is less than or equal to 14, my alternative hypothesis, the complement, is U is greater than 14. and it doesn't have the inequality, so that's why it's the alternative hypothesis. Okay, that's as far as we're going to get in this video. We'll have a second video that will explain to us what we do with these hypotheses. Okay, so I will see you then.